All right, ladies and gentlemen, welcome to week 15, last Monday live session, 61C. Woo! Great to see you all here. Delightful, delightful. Do know this, I'm going to say it early and often, like voting in Chicago, or vote early and often. Make sure you come on Wednesday for a live session for James, our awesome guest who's here, is going to give a live session on GPUs. Come here, same bad time, same bad channel. And also make sure you come on Friday for our last live lecture. So this is 3 live. It's as if we weren't even in a virtual world and we're just having live sessions Monday, Wednesday, Friday, the same time, okay? 4 to 5, come the same channel, same link. We'll see you there. Perfect. But by the way, Bora, we need to make the actual webinar. Let's not forget to do that.
I'm on it.
We may have forgotten to do that. So let's make sure we do that.
I'm on it. And,
all right.
Yeah, beautiful. And we'll have also the award, preliminary awards.
Yes, and the awards happen.
Friday.
Remember, the awards are going to happen on Friday, so we're excited about that. All right. Today's agenda, we always do the agenda here. Welcome to week 15. Where can we 14? Cross that up. Can you fix that in post, Bob? Yeah, sure. Week 15. Our guest is James Percy from Apple Computer. We're going to have a couple of computing the news pieces. We'll talk about important final exam information. We're going to drop a mic on some of that stuff, and then we're going to do a review of the schedule, and then we'll have an Ask Us Anything, and we'll have some time there. But let's jump into our wonderful guest, James. So our guest is James Percy from Apple Computer. I'm going to now add you to the spotlight so you're on stage. Welcome, James. Great to see you here. James has been involved in computer engineering in many roles. I think since your undergrad at Princeton, I'm thinking back to the time. He was an engineering manager, you can see here at ATI. Then he went to AMD as the director of engineering. And then joined Apple since 2013, has been the GPU leader. So he's been one of the key, like as you get up in the top of the pyramid, the group meetings become smaller and smaller. And James is in smaller and smaller group meetings with more and more important people. I'm sure you're meeting with Tim Cook every other week or something like that. I'm just crazy. But anyway, it's James, it's been great to have you. We've been working together this last semester, thinking about this. And he also has been a guest at 61C a year ago. So thank you again for returning to 61C. The purpose of this is just to meet you and get to know you and talk about kind of your path and advice you have for students and who are thinking about similar careers or thinking about your time back at a school. So first of all, I always start with, how did you get to where you are? How did you even, I'll just throw a couple of questions out there. Did you always know you wanted to be what you are now? And if not, how did you get to where you are now? So kind of tell us your path, tell us your career path.
Sure. I'll try to go through
that. You can go as far back as you want to. In second grade, Mrs. Hockenhauser always told me I'd be a great engineer. No, go ahead. Anything you want to do.
Yeah. So going way back, I was always interested in computers. Going back as far, I forget how old I was, probably 4th or 5th grade, which would have been in the 80s, believe it or not. Interested in computers since I was a kid. We used to play computer games. Back then, you'd have to run stuff on DOS, and you'd have to set it up to manage your memory and stuff like that. And so that got me very interested in like how do computers work and how do operating systems work. And back in those days, you really had to kind of hack your way through just to get games to run. And so that was kind of like my early interest in computers. And that kind of turned into me becoming a computer science major in college at Princeton. And I went into Princeton knowing I wanted to be in engineering. I liked math a lot, I liked physics a lot. I discovered that like real math, meaning studying math in a university, is really hard, like really hard. And despite being very good at it, I was not that good at it. And so
that's my story too. I was like a superstar in high school, and then, wait, this math is a lot harder than it was in high school. Yeah.
Theoretical math is hard.
Right.
And so, but I did take an introduction to computer science class the freshman year of college, and I'm sure these days people take that stuff in high school or in middle school or earlier.
Sure, but sometimes not. There are people who don't get it, and we're here for them. We teach a class. My BJC class is exactly that space to introduce to people at college if that's their first time. We let people into the.
So I was learning how to code in C freshman year of college, and I remember half the people in that class had been doing it for years, and so I felt woefully behind compared to at least half the class, but I worked really hard at it, many late nights in the labs, and I realized it was was really fun. I really enjoyed it, and I was pretty good at it. I was able to, once I kind of got my heads around the basic constructs of like, how does a C program work and what is a pointer and stuff like that, and what's a function call. I really enjoyed it, and
you feel powerful, like something about C, like something about being low level. Like I can do anything. I can move bits around in any way I want to, right? Different than
Exactly.
Python, you're 10 miles up, somehow below it magical, right? But really being low level, we love that. Yeah.
And so that turned into, okay, well, this is cool. How does C work, and like how does assembly work, and then how do you boot an operating system, and how does networking work, and how do graphics pixels end up on screen? So I literally just took every class that I could reasonably take about computer science, and I took operating systems and networking systems and computer graphics and compilers, and learned about how assembly works and RISC architectures and stuff like that, and really just absorbed as much as I could. And I discovered going through that kind of sophomore and junior year that I was really interested in computer graphics, and so that's kind of what I specialized in terms of. At Princeton, you do, even if you're an engineer, you kind of do a senior project or 2 senior projects. And so that's what I focused my my senior projects on. And I learned about ray tracing. I did some kind of advanced ray tracing algorithms. And the cool thing I liked about it,
from the software point, I mean, we have CS1D4, our graphics class, but it's always software. We're never getting into the hardware behind it ever.
It was all kind of software programming and OpenGL and kind of application level. But what I really liked about it, and I'll get to the hardware part in a minute, but what I really liked about it was you drew pictures at the end, and the pictures looked really cool. And for me, it was easier for me to think about like, hey, here's this model, and I want to come up with an algorithm, and it generates a picture at the end of the day. It wasn't just bits moving across a network.
Right. Yeah.
I could actually kind of,
it's art in a way, right?
That's beautiful. Was part of our assignments. We actually had to do assignments using the algorithms that we had learned, but it had to be artistic. It had to look cool, or it had to be creative.
Did they give you more points for looking cooler? Like that's actually, I've never seen that. Where they actually give you, that's really
there were
more points for,
there was a contest at each lab assignment for like the best looking image or picture or whatever it was. So there was bonus points for being kind of creative. And so I really like that too. And so my advisor at the time was a guy named Thomas Funkhauser. I think he's
that's my buddy.
You know,
So we were grad students together. That's my buddy.
Are you serious? Oh, wow.
Seriously.
Small world.
You're a young guy, but we were like sitting together. He was awesome. Are you kidding me?
I probably wouldn't be here if it wasn't for Professor
Look at the small world. Look at this world.
He hooked me up with a guy named Mark Siegel, who knew a guy named Bob Drevin, who was working at ATI at the time, and said, hey, I know this guy, James. He's a CS guy. He really likes graphics. Hey, you should check it out.
Yeah.
And the reason I tell you guys that is it's never underestimate the value of the contacts that you're going to make at university, because it could be Dan knows a guy who knows a guy who about a job that you might be really excited in. And that was basically what got me into ATI. And I basically got a job doing verification of graphics hardware, having really no idea what that meant. Like all I knew was that I wanted to work on graphics somehow, because I was really interested in graphics. ATI at the time was one of the few companies left making what we call discrete graphics cards, meaning GPUs or chips that are just dedicated to accelerating graphics algorithms. And I was like, hey, that sounds pretty cool. I'm really interested in this. Let's go find out what this is about. I had taken basically the prerequisites for electrical engineering at Princeton, but I was not an electrical engineering major. And I remember showing up the first day of my job, and they started telling me about like tape outs and synthesis and net lists. And I had no idea what any of those things were. And I asked Bob Drevin at the time, hey, what is all this stuff? And they were probably like, oh my God,Ike, why did we hire this person? Sorry, this is the long version. I'll try. No,
that's fine. No, go. That's great.
That's good.
Go ahead, Bori.
It's very. I think there are a lot of people here who can relate to that.
Yeah, right.
In many different ways. Keep going.
And so I was basically a CS software guy, kind of like in the hardware organization at a hardware company. And what I brought to the table at that time was that I knew how to code in C and C++, and I knew graphics algorithms. And so what I started out doing was I actually worked on writing kind of low-level C tests for different blocks inside the hardware, and also kind of working on some kind of top-level OpenGL-like tests. and to be honest, it isn't probably truly what we consider verification in the honest sense 20 years later, but it was low enough level that I could read the hardware specs and I could understand, okay, this is how this interface to this block works. This is what the inputs and restrictions are. We compare it to a C model, which I also worked on, and that was how we pipe vectors through, and when the vectors match on the output, then you're good and your block's done. That's not necessarily how DV gets, or verification, hardware verification gets done today. But for me, it opened up a.
It's a higher level. It's a high level verification. It isn't low level. It's upper level verification.
It's higher level, and it's something with somebody with a C background and who understood how some of the math or graphics algorithms worked could do. And so that's how I got interested in hardware. And so I started my first couple of years at ATI, to be honest, were some of my funnest of my career, because in those 2 years I worked on production OpenGL drivers, I worked on emulation platforms, I worked on diagnostics in the lab, I worked on the C model, I worked on verification. I worked with some guys at Stanford at doing a ray tracing demo on some new hardware that we had that hadn't even shipped yet. So I mean, I was doing all sorts of different stuff. And so I was really just like a sponge learning about all these different things. And eventually I kind of decided, hey, this is pretty cool, but I think if I'm going to stay in this area, like I really need to understand hardware more. And so I became a manager of the verification team. And at the same time, I actually started taking a couple classes at Stanford on kind of introduction to logic design. And some of that was kind of a refresh from what I had at undergrad that I hadn't looked at in a few years. And some of it was kind of getting a deeper understanding of like what it takes to productize hardware, which was far outside my comfort zone.
Was it, what was it, 272, 273, or?
I think it was 272,
like
if I remember. It's been over 10 years, but by name, I think that was that's what it was.
Right.
And so I wasn't pursuing a degree or anything. This was purely just so I could kind of get a better understanding of how hardware worked. And I kind of parlayed that into starting to manage like part of the design team. I started managing GPU projects at ATI. And kind of learning, that was just trial by fire. You kind of learn about what does it take to actually build a chip? Like, what are all the things that you have to worry about? Not just like, hey, do I have my algorithm correct? But can I actually place and route it? Can I close timing on it? Can I cool it?
Can I
cool it? What are the power delivery problems? What technology node and what transistor mix am I going to use? I mean, you can go on and on about the amount of things I learned in those couple of years managing projects and learning from people who had been doing this for years. And then AMD actually acquired ATI, I think back in 2006, I want to say 2006 or 7. And I kind of was doing the same thing. Managing a larger team. Then I also started working on what we called APUs at the time, meaning they were one of the first types of SoCs to combine CPUs and GPUs on the same chip. And so I was kind of responsible for the GPU part of that chip.
What's the A? What's the A stand for? That is that like all inclusive?
What
did
it stand for?
Application
processing unit. Yeah, I think that's what it was. And now, of course, fast forward 10 or 12 years later, everybody is doing these chips. Apple has been doing those chips, and we see there's huge energy efficiencies from putting GPU and CPUs on the same die, along with a whole bunch of other stuff. That it's like everybody's doing it. But at the time, it was pretty novel and pretty exciting and very hard. And so I stayed at AMD up until about 2013. AMD was having a rough time, unfortunately, at that period. Things are much better now. And I came to Apple because Apple was starting to build or wanted to build up GPU capabilities in-house. And so at that time, Apple had already been shipping iPhones with their own SoCs, their own CPUs, but they were kind of expanding into GPUs and other areas as well. And so I said, hey, this feels like a really good opportunity. And I'm gonna give it a shot. There's a bunch of people that were already at Apple that I already knew, so I was going to a place that was somewhat comfortable.
That's nice.
And I helped build up the Cupertino GPU team from about like 4 or 5 people at the time to 70 or so people today.
Whoa! Wow.
That's a big team. Actually now I've actually just taken over responsibility for all of the what we call GPU IP development at Apple. So what that means is like kind of front end RTL microarchitecture and verification is now my responsibility. So now I'm managing a 200-person team across multiple sites.
Holy moly!
So,
Is there engineering that's not in Cupertino?
oh yeah, there's lots of engineering outside of Cupertino.
Oh, okay.
So in Austin, my boss is actually based in Austin.
Oh.
And so there's a team in Austin that I'm responsible for. There's also GPU physical design. There's kind of architecture validation that I'm not responsible for. That's based in Austin. We have a site in Orlando. We have a site in the UK. We have not GPU related, but there's a site in Israel, in Haifa and Herzliya. So we are all over the place.
And we didn't know about the GPU until like 3 or 4 years ago, right?
Yes. So we went public, or the first time we said we shipped our own Apple designed GPU was with the iPhone 10 in 2017. And so my team had actually been working on kind of pieces of the GPU prior to that. But it wasn't and we shipped as well. Like we shipped a new texture unit. I forget which iPhone it was, but we'd been shipping pieces of it for quite some time. But we kind of did our first from scratch design with the iPhone 10. And as you guys probably, if you follow the news, not only are we doing iPhones and iPads, we're now shipping in the Macs now as well.
Right.
So
Right.
my wife has one upstairs, but I have one. And it's absolutely amazing, the experience of a Mac with Apple Silicon. So if you don't have one, I encourage you to get one.
And it's still holiday season. It's still,
Yeah.
That's outstanding. I'm curious how do you I'm looking about a team of 200 people. How are you in meetings every minute, or do you have subgroups? How are you able to manage such a large group just to get I mean, and you're working people above you, like you're at a layer, right? So you're talking to people above you who are calling your meetings, and you got to call meetings for people below you. You can't be meeting every 200 person once a week. So how are you able to manage all that?
Yeah, it's pretty hard to get on James's schedule. Just so
but students don't realize who we're getting for this semester. These are big. It's kind of a big deal. I'm just saying, it's kind of a big deal. This is exciting. That's great. Thank you for your time.
Yes, I am in meetings almost all day, every day, which is a challenge, especially early. I'm not really a morning person, but a lot of the folks I work with are in the UK and the East Coast. In terms of managing a team like that, and by the way, this is a pretty recent change, so I'm still kind of learning how to manage this and how I want to run it. But you really have to have a very strong staff that you trust and that you believe in, and so you can delegate tasks to that you're confident they're gonna get done and come to you when they have problems that they need your help with. And so Apple's an interesting company in the sense that clearly, given its size and the number of things that we're doing, delegation has to be a thing. But you have to learn how to delegate, but still be in the details of the things that matter. So I think people that are kind of mid to senior levels at Apple have become very good at that. Clearly, you can't dive into anything. There just aren't enough hours in the day and in the week. But you have to be very good about choosing which things you want to dive deeply on and get involved with. And
the important things.
That's a skill I am acquiring.
It's like a performance. You're going to increase performance. You increase the thing where the time is being spent slowest. That's the thing you increase to make the biggest performance. Here, you spend your hours on things that are really the things that matter the most. You make a decision. What can people just do without you needing to touch? What do you need to really get in to work on? That's great.
Right. And you have to kind of train your team or your people to make sure they're bringing the things to you that matter the most and that need your input, and are not bringing things to you that either are not important and don't matter, and are also not hiding is probably the wrong word, but may not be giving you the visibility of the things that you need visibility of. Sure.
I'm going to ask a weird COVID-y question. I'm sure you're working from home now. Are you actually go to Apple Park, or how are you? How do you manage that?
I am working from home. I have a virtual background because I'm in my guest room because I got kicked out of my home office from my kids.
Many of us did too.
I've been into the office probably 5 or 6 times, maybe once a month, I'd say on average. There's not a strong need for me to go in unless there's something special that needs to be taken care of. And generally we're unless people want to be in the office or need to be for very specific needs.
Right. I mean, that's what I say. Hardware people, I think of needing to be in the lab. Like whenever we see the videos of, oh, here's the new chip, and I see this lab, you got to be in that lab. You can't just do that at home. Yeah, I'm at the kitchen table. I'm trying to make the new GPU. No, you got to be in the lab with the sensors and the.
You'd be amazed, actually, that even many of the people that work in the labs these days actually don't need to be there in person. I mean, clearly we need to have a couple people in there to set them up, but initially, but a lot of the debug can be done remotely these days.
Out of here. That is so cool. That is so
very, very impressive. And it's actually, we've had to develop that technology anyway because of the multi-sidedness that we talked about earlier. So we have people, we've always had people in Austin debugging chips and systems that are physically located in Cupertino. We don't like shipping pre-prototype material around. Or people
lose them on a bar in San Francisco. Remember those? How many times we saw
I remember that. Yep.
I remember that. I just left under the counter. Sorry, it doesn't happen.
So so we've had that capability, but we've been leaning on it even more, such that we can do a lot of remote debugging without having people being there in person.
Wow, that's impressive.
That's cool. Just for everybody's info, even our research chips, I mean, that are even, clunkier, when they come back, I mean, they're always clunkier. These are not products. We test them mostly remotely. I mean, somebody goes in and, gets it through the smoke test. I mean, there is a funny thing about the smoke test, right? I mean, when you power it up, will it puff?
Oh, is that what that's called? I actually didn't know that was what that's called. The smoke test. Put some power, does it actually make smoke out of it? And that's bad. Smoke is bad, I'm guessing, right?
Smoke is not good.
Just so we know. Yeah. That's beautiful.
So once when you pass the smoke test, and if you manage to boot Linux on it, I mean, it's all remote. I mean, you get the terminal and you can be anywhere. I mean, with us, it's a bit of a challenge, running stuff through campus security. I can just imagine how fun is that with Apple's security, doing these kind of things. Oh, I want a Docker image. No, you can't have a Docker image.
Right.
And so on.
Yeah, I guess that's true. I mean, you're probably, I don't know, was this always the case that you're in such a high security kind of a thing where your stuff is cutting edge, and if that gets out, that's the company? I mean, or that's a big hit. Like, have you always been in that space, or was it a big deal as you kind of moved up, like to be in more, like now it's iris scanners? I mean, like what's the level of security when you go in terms of keeping this IP, within the walls of the company?
We are very selective and careful about any sort of IP that leaves the walls of Apple pre-production or before it's been released to the world. So I mean, and there's special carrier programs that are set up for that, and they're typically only people can carry stuff around once things have been announced but not shipped. So we did have to make some special provisions, I'll say, for dealing with what that looked like in a COVID work from home world. But we did let people do it. I mean, we weren't gonna. You guys have probably seen all the stuff we've announced the last 3 months. That stuff would not have shipped if we did not let people bring it home. So it was something that had to happen.
Wow. Right. That makes sense. Yeah, that makes sense. Yeah, you can't ask these people to always come back in. Yeah. That makes sense.
Things are out. I mean, you can see, I think E-Times now has on the cover page, there'll be a series of articles of dissecting M1 chip, and they're going to take
every single part. Disassemble it. Yeah. Wow.
Mini, I mean, no, but this is, decapping the chip and, dissecting.
How did they do what they did? Yeah. How did they do what they did? Right.
Yeah, and we're particularly sensitive about like performance benchmarks and people getting data and results that are not not production quality. So we want to, in addition to just the surprise and delight we want to deliver to our customers and being delighted by the experience, we also want to make sure that we're only high quality data is getting out there.
Sure. Makes sense.
Okay, we have a bunch of questions.
Yeah, we have some questions. This is great. Thank you for all this background stuff. Now we'll just do Q&A if we can. So this is wonderful.
Absolutely.
There was just an anonymous question. It says, do you code or design much anymore, or is it just management?
No, they don't let me code. They don't.
Oh no, just meetings. Oh, it's so sad. No,
it's actually
hard.
Interesting. Back at AMD, up until I left, I at least still like kind of had a tree and knew how to build it and run simulations and run tests. And coming to Apple, and I came into Apple as a management position, and despite it being a small team, I was not really, I never had time to really get used to the flow or really learn how things work. And so kind of not having that background of having to growing up actually contributing to the code line and how projects were actually organized in the code line, I never really had the chance to learn that at Apple. So I tinker on a little bit on the side myself, and hopefully you'll get to see that on Wednesday if we're able to do that.
That'd be great. That'd be wonderful.
I have not touched a single transistor personally on anything that we've shipped, unfortunately.
Sure. Wonderful. This is a great question from Adrian. What are some advantages of creating your own GPU versus pre-made GPUs? Give me the best case, like the most salient thing of like what your thing just blows away a pre-made GPU versus something that you can optimize for your own workload.
Yeah, there's a long answer to that and a short answer. The short answer is performance and really performance per watt that we deliver to our customers that the end users actually see. Now there's a longer answer to that that's related to features and optimizing for the features that we want and having control over those features. That is also true, but really at the end of the day, we just felt like Apple wanted to control our destiny when it came to the GPU and really the experience that our customers had and our ability to differentiate between our competitors really relied on us owning the GPU and owning our own design. And you see that in what we ship today, both in the phone and the pad and now the Mac space. If you compare the MacBook with the M1 to what we were previously shipping, both in the CPU space, by the way, CPU and GPU space, it just blows it away by multiple factors. So really what we care about at the end of the day is the performance and the experience we deliver to our customers.
Mm-hmm.
By the way, related to that, and I tell us if you can't answer this, there are a few questions on our Piazza about this unified memory architecture and 128-bit bus that I try to answer. Can you say something about that? What's a unified memory architecture and what's up with the 128-bit bus?
I'm not familiar I'm not familiar with the questions around the 128-bit bus, so I probably can't answer that. The unified memory architecture there's a number of things that are good about it. And it was something that, frankly, AMD was interested in as well. But typically, if you look at a CPU plus GPU system that have separate memory spaces, you have a lot of copies from the CPU to get data to the GPU so the GPU can use it and access it at high bandwidth and relatively low latency. But the problem is that those copies back and forth from CPU memory space to GPU memory space are expensive and can often be the bottleneck of your performance. And in addition to just having performance issues, there's also power cost to doing that. So what you find is in a unified memory architecture where you can avoid those copies, you not only get better performance, you also avoid the energy cost of copying all that data around. And it's also a simpler programming model for software to use. And so it has multiple benefits when you look at it compared to a non-unified memory architecture. Is that?
I was pretty close on that, although I'm not quite sure on the simpler programming, right? Don't you have to now be careful about pinning things and stuff like that, so that it doesn't escape back to the SSD?
You have to be careful about, and I probably need to be careful about what I say here, but you certainly need to be careful about race conditions. Let me put it that way. And so the driver in our software stack has to be aware of avoiding creating race conditions. But the API, the GPU API is pretty good about being explicit about those. Hopefully that was a somewhat vague answer.
And Dan actually covered some of that, in terms of multiple CPUs, I think in last week. So this is pretty good. I think people can connect the dots now. How does this actually work? But yeah, this pinning stuff is going to be, it cannot be swapping. Okay, more questions. I think
Sure.
we got
Benjamin has a good one, which is what changes in power management enabled the latest Apple Silicon MacBook not to have a fan? I mean, it's just so amazing that you're able to get all that space back and put a bigger battery and all that without a fan. How did you do that? That's an incredible. I mean, I've been burning my lap on Apple laptops for 20 years. Yep. How did they do it? How is that? That's incredible.
It basically boils down to what I said before about performance efficiency and energy efficiency. Right. And so,
but it's not a sacrifice. It's not like, well, let's sacrifice it just to cool it down. You're able to get better performance, but yet cooler. Like, how is that? That's like, seems like it's mutually exclusive. You can't have, you get one of the two: great performance, bad heat, or low, no heat but low performance. But how do you do both? That's the kind of question I think.
It really comes down. I think it comes down to all of the techniques that Apple has built up over multiple years from building low power SoCs for watches, phones, and iPads, and then applying those techniques to a kind of Mac class platform have enabled us to do that. So it's not one single thing that you can point to that said, oh, Apple did this, and that was what allowed us to build a fanless MacBook Air. Right. It's really, and this is what makes it hard, is that it requires a enormously large coordinated effort across software, across architecture, across the design team, with the technology team, with the team that builds the physical cooling solution, because there still has to be some sort of dissipation thing in there, even if there isn't a physical fan. All those different teams, and I left out many of them, but all those different teams have to come to the table with their best foot forward to really optimize around power efficiency. Because without doing that, then you don't get the type of products that we get. And so it's not a silver bullet where if you just go do this one architecture change, boom, you'll be able to deliver the performance that we deliver at the power profiles that we deliver. It's really a lot of effort across a lot of different teams that make it happen.
And I guess you probably can't answer this, so I don't mean to put you on the spot, but it almost feels like, did it come from the top? The guy, Tim, said, I want you to make a blank, a MacBook Air that has no fan, or did the engineering, and somehow there was like a eureka moment where we started looking at the numbers of cooling. He's like, wait, we think we can do this. And then it bubbled up to say, hey, make sure to advertise it, because we're trying to build this crazy thing. So did it come from bottom up, or did it come from the top down? I don't know. You say top down or bottom up. I don't know if that gives away too much. But it'd be cool if it were bottom up. Like, oh my God, some engineer at the lowest levels, like, I ran the numbers and we can do this. And then it bubbled up and then people got excited about it. Or did it come from a visionary?
I honestly don't know.
It's such a big deal. It's such a big deal. That's all.
In fact, I didn't know that the MacBook Air that we just shipped was going to be fanless until it was announced.
Come on.
Wow. Because the interesting thing is
that's a good secret.
I know everything about the chip specs and what we need to build the chips.
Yeah.
But whether or not and this is an interesting thing about Apple, but whether or not there's a fan on a particular system, there's no real reason for me to, as the GPU silicon guy, to know that. That's right. All I need to know is this is the power profile that we're targeting for. Right. Like, and how much performance are you going to deliver at that power target? And it's really up to the system team who's building.
Phones have no fan. I mean, my phone has no fan, right? So I mean, right? I mean, so and it has a big old piece of plastic in the back. Apple, the silicon thing that doesn't. There's no way. Where's the air? Because that's a speaker. Where's this getting cool, right? I mean, so they're able to do it for other pieces of hardware, not necessarily. Yeah, not bigger ones. That's great.
We're running fairly low on time because we have a few other things that we need to cover. I do have a couple of questions. I mean, there are questions that came in about the management. So you're apparently, I've learned that you do hire quite a few full-time employees and quite a few interns in your group. Obviously, I mean, these people, this pretty big group needs to come from somewhere. I've just learned, I think Jared told me that they are either gone through or are going through these internship applications. Do you have any tips for interviews? How do you interview? What happens in these interviews at Apple?
Yep, excellent question and comment. The number one thing with any interview, not just Apple, but I think probably for any interview in any job, is be prepared. And so what I mean by that is go ahead and ask your recruiter or your manager, hiring manager, if you have access to them beforehand. Hey, what's the interview going to look like? The worst thing they can say is, hey, we're not going to tell you anything. Although I don't think they would say that.
Right.
But like, what types of questions should I expect? What languages should I expect to code in? Know your projects like the back of your hand if they're on your resume. One of my favorite questions that I like to ask intern and new grad candidates is, tell me about the hardest project that you've ever worked on. Why was it hard, and what did you learn from it? There's lots of there's other people on my team will ask you coding questions, but I want to hear about like what kept you up in the lab for 2 days in a row, and what did you learn from that experience. The candidates that have not done well with me, frankly, will have some project that they did a couple years ago on their resume, and they either can't speak to the details of it, they don't remember, or maybe their friend did most of the project, and they weren't very involved. That's not good. That's not good.
Yeah, we've been telling them that for since the beginning. You got to know all projects. Exactly.
So be prepared to speak to and talk about anything that's on your resume, any language that's on your resume, be prepared to code in it. Any project that's on your resume, be prepared to talk about it and explain it in a lot of detail. Because those are the things that people want to hear about. And frankly, it's much more interesting as an interviewer to hear about like hard projects and things that maybe didn't go that well and that were learning experiences than just asking, hey, can you go code this C program or Verilog question or pick your favorite language. Sure, there will absolutely be some of that. You should be prepared, but if you're a good candidate, that stuff will come easily. And it's the projects and the experiences that will really set you apart from other candidates. The other thing I'll add to that is also, if you have prior internship experience already, that's great. But same thing, be prepared to talk about it as long as you can. I respect there'll be some confidentiality issues there, but if there is something you came away from that internship that was either really challenging that you liked a lot, or maybe even you didn't like, you learned that, hey, I don't want to go be a diagnostic person in the lab for whatever reason. Like, say why. That really kind of shows us something about the way that you think, that you have opinions about things. Having an opinion about things is great. You don't necessarily have to agree with your interviewer, but like showing that you can actually think independently and you have opinions about something and you can defend those opinions really goes a long way to show you as somebody that has a lot of potential at Apple. So that was kind of a long-winded answer, but those were some of my thoughts there.
Nice. Do we have time for any more? Or is
that's great. There is another one. I mean, what I've learned also is our students, apparently those that interviewed for firmware positions, aced it. So that those have been filled, taken in a week. I mean, they were sucked. 61C students sucked, or TAs sucked out the air out of that room. There is not, that was solved.
Great job,
quickly.
Team.
But you told me that, very good, the C thing is pretty useful, and assembly too comes in handy. But you mentioned that your path to what are you doing now came through verification. We don't teach verification. Do you have a hint? Should people be scared if a verification group approaches them and says, hey, can you come over and work with us on verification? What should they say?
They should not be scared. Nobody taught me verification either in college, so I basically learned it on the job. I think as many people do, although not all. There are verification classes out there at some universities right now. Verification is a fantastic field to get into, and one of the reasons is because good verification engineers are extremely scarce. And you can use the laws of supply and demand to figure out what that means. But if it's something that you are interested in and passionate about, you can really have a big impact on products. Because if you've got some critical bug that you can't ship with, or you have some horrible software workaround that impacts performance, like that's a huge problem and gets a lot of visibility. In terms of what you need to know. To become a verification engineer, you don't have to be a UVM guru. You don't even have to necessarily be a system Verilog guru at right away. All you need to be good at is coding in some reasonably modern language, and you will be able to learn UVM or system Verilog or OVM or pick your other favorite verification language. If you're good at C++, you can figure out you'll be able to figure out the other things. What you really need is to be able to ask good hard questions, think through problems, challenge what you're given, such that like if somebody throws a problem at you, you can ask the right questions to get to the bottom of it. That's what makes a really good verification engineer, challenging the specs that you're given. Like, hey, does this really make sense? And when we put these two hardware blocks together, are they really going to work? It's having that sort of a inquiring mindset that will make a good verification engineer.
All right. Thank you. Thank you so much.
Thank you so much. The students, let's give James a hand. Thank you so much for your time together with us, James. Woo!
Thanks.
Wonderful.
James Percy.
And by the way, please do come.
On Wednesday.
Yeah, on Wednesday. Come back, everybody here. Make sure you tell your friends. Come on back to this channel at 4 o'clock. And James will be giving a live lecture on how GPUs work. Exciting stuff and what they're used for. Thanks again, James. Take care, my friend. That was great.
See you
Wednesday.
Take care.
All right.
Bye.
Perfect. Okay. Bye.
Bye.
All right. So let's do a quick. You got about 8 minutes left. Let's do Computing the News. I found this delightful story of Computing the News about a new app that uses computer vision and certainly a neural net trained on different models of food and caloric content of those models of food, to be able to instantly take a picture of your food. And people do this when they go to fancy restaurants anyway, but to actually extract the caloric content. So I guess you'll serve yourself a plate, say, I'm going to eat this plate, and then you take a picture of the plate and it estimates the distance and the time and the size of the scale of things, and then figures out all the calories you're eating. So that's really important for people who are on limited diets or diabetics.
Figuring out how much oil or fat is in the gravy.
Right. I don't want to know. I don't want to know. And certainly you can make things with, I mean, like it's really hard for curries because you can make, example, saag paneer, which is one of my it's an Indian dish with spinach and cream, and you can put a lot of ghee and cream in it or less if so. You make it kind of with water or more creamy. And that little choice, I don't know how a camera would do it. So I like this idea for big things, but I certainly don't think it's going to be the end all be all, because I can make 10 different recipes, one with like basically none of the heavy fatty stuff and one with a lot of it, and it wouldn't be able to tell the difference because it looks like a big curry or a big saag paneer. So I don't know how accurate this is going to be, but we'll see. The second one, maybe Bori, you could share some of these things for the second one that I'm highlighting here. Oops, I'm clicking on it. Click. Oh, I did the same one. I did it twice. There's another one that I guess I lost the slide, and maybe. Oh no, here it is. Yoink, there it is. All right, sorry, I had two duplicate slides in there. A chip delivers smarter, light-powered AI. And I actually visited, this is the Australia's Royal Melbourne Institute of Technology. This is in Melbourne, and I visited them when I gave a talk when I was there in 2007, a million years ago. It's like one of the top, institutes of technology in Australia. They're downtown Melbourne. But in theory, they have an AI and a single electronic chip. Do you know anything about this or some of that work?
Yeah, I mean, I don't know exactly what it is, but you guys in your projects 2 and 4, you have figured out a lot of stuff that is happening when running neural net inference. So generally, what they call AI is neural net inference or machine learning inference, and what you'll figure it out also is a lot of there is either running convolutions or matrix multiplications, and you guys become pretty good at that by using standard digital hardware.
Classified numbers. Wait, have you seen that before? Right.
Yeah.
You're welcome, by the way. You're welcome.
Yeah.
Right. So
no, people have figured out that they can do that on different hardware, right? You can build specialized hardware that is really good at doing matrix multiplications. Now, the problem there is that hardware generally does not do other things, like for loops will, or whatever other things are needed there. There are other functions that are in there. So you need to have some kind of a CPU and a well-integrated accelerator. That accelerator can be made of, I don't know, light or some kind of a crazy memory or anything that, what you'll find out, anything that satisfies Kirchhoff's laws and has nonlinearity is able to do multiplication, right? I mean, you get the second order nonlinearity for free, and it does, some sort of multiplication. Sophia Shao teaches a class. You guys are not quite ready, but I think there is a big interest in this class. ML hardware or AI hardware, and they touch on. I mean, she has half of the class are guest speakers that come and bring their either conventional, really big matrix multiplication thing like a TPU that we have mentioned in the class, or their funky hardware and people from Mythic, I think, came and talked about their analog matrix multiplication. Mythic actually just started shipping right now. So the jury is out which one of these is going to actually work. I was told that there were 700 startups trying to make something that is going to do matrix multiplication faster.
Wow. Wow.
7th in the Bay Area. I mean, matrix multiplication, put it this way, neural net inference faster. We're going to do your project 2 and project 4 faster than you can.
Right. That's great. Good stuff. Good stuff. All right. We're up to the next one. This is I'm going to try something. I guess I can't do it. I can't block it most of the bottom. Here's the thing. The next slide topic is final exam information. We have a bomb to drop. The bomb to drop is the final exam was scheduled for 12/13, a Sunday, all 24 hours. The campus sent a big memo to everybody saying that you cannot offer a final exam outside of the final exam schedule and don't make willy-nilly arbitrary changes. Well, sorry, campus, this was not an arbitrary change. We had this since the first day of school, and we let you all know that, and you planned for it. But they said, well, they said back to us, sorry, you have to have it on the day that it was scheduled, and we have to acknowledge that request. So you now have, maybe this is good or maybe this is bad, you now have 4 more days to study. But instead of having your final exam on a day where there's no other exams, you have your final exam on a day when there are other exams. And so your final exam is now going to be on Thursday, December 17th. And you have 24 hours to do your final exam as before. And we'll talk about the time limit of that. But that's what's on the schedule. So you're like, wait, why is 61C saying one day when my final exam schedule says one? No, we have to honor the final exam schedule. By the way, in spring 20, we were able to move our final exams out and it was no trouble. But I think that's because it was kind of a special semester, and this is a semester that's been online since the beginning. And so maybe that's a little different. But we said, well, we did it, in CS10, we give in fact, even CS10, we have one part of our final exam on the Sunday still, that Sunday before the final exam week. But they basically said, no, you have to have a final exam during the time. And so we have to honor what campus said. So this is not our choice. Yeah, this is just basically deferring to campus.
There is a clarification question here, right? I mean, the campus memo said that we have to hold the final on the time, on the date and in the time window when we are supposed to, which is 8 to 11 a.m. on Thursday.
Right.
But
they also said,
however, they gave us, yeah.
They also said we encourage you to have alternate times. And so that's what allows us to have the 24-hour window. And so they're actually strongly encouraging us to have flexibility. In fact, we just had a survey. Bora was in our EECS faculty meeting this morning. We had a survey that maybe it was last week that said the students want flexibility for their exams. That is something that's been shown to not, don't just make me proctor and be there exactly the time. Give us some flexibility for the time to be able to take a rest and all those things. And so that's kind of what we're doing. That's what we've been doing all along. So it's exactly the same format. You are going to have a limited time like we had the midterm. And in fact, here's the next slide, the big one. We certainly want to honor and thank the student representatives for their feedback. That's been so wonderful this last couple of weeks. And they've encouraged us to think about scaling this down to be a 3-hour window. And that was actually helpful for us to be able to now honor the campus. So they kind of the two pieces came together to both agree that it makes sense to keep this being a 3-hour exam. So we're going to have it on the day. We're going to offer exam that will take you a total of, you'll have no more than 3 hours total. You can take it in one sitting. If you want to do 3-hour sitting, you can take it from 8 to 11. So if you say, hey, campus, yes, I'm see, look, see here, I'm honoring you. You asked 8 to 11, I'm taking it. You can take all three spots exactly as a normal exam would be. You can also do what we suggest, which is take in any order, take one of them, take the second, take the third, take a break between it, eat lunch between them, figure it out between other exams. I know it's not the best news for everybody because you were hoping to do it on the Sunday aside from other exams, but we'd have to do this on the day of. So we're doing on, as I said, the 17th. And we broke them into 3 pieces. Here's the 3 sections. There's going to be a quest, which is going to be the quest clobber. There'll be a question called quest clobber question, a midterm clobber question, which is contain all the stuff from the midterm that isn't on the quest. And then everything is the final, which is everything past the midterm. That's it, those 3 pieces. We realized as we were thinking about the load of this is that more material happened in that midterm window. That was just a ton of stuff in that midterm section. A little less here, obviously caches is big, VM is big, the parallelism is big, but we're going to put those into smaller questions so that we're going to decide the time to be 90 minutes for the midterm clobber and 60 minutes for the final clobber. And again, overall, that's 3 hours. And we're going to ask that our TAs are able to ace those exams in a sum of 1.5 hours. So we're going to hope, and we'll be publishing those stats. CC was very good about collecting those stats for the midterm and then publishing that. We'll try to do the same thing and share what the mean is, what the max is. And by the way, if the TAs can't do that in half the time, 15, 45, and 30, we're going to cut more material. We just keep cutting until our TAs can get it down to half of that time, and then we'll give you double the time. That's the current plan. So hopefully be able to finish within those 3 hours. Yes, Bor.
Yeah. I mean, these are currently draft times, proposed times 30, 90, and 60. Based on how our TAs do, we may switch. We may change, and we may have 30, 80, 70, or something like that.
That's true. Yeah, this is the current design plan. This is even as it says, current plan. We don't think we're going to change from a 3-section plan. We think that's locked in. But those times, those 3, which are right here, these 3 times are going to be maybe adjusted depending on what our TAs are telling us in terms of difficulty. But we're trying to cut. That's all we're doing. We're just cutting. We have ideas, and we're just like, here's the block of text. How small can I make it? The setup before we ask you the question to do that, and we'll do that. And by the way, we're going to try to have this graded instantly. The nice thing about Prairie Learn is that if we code the solution into, you won't see it. You'll do it like you'll see nothing different. You'll take the exam like you normally do, rather than waiting 2 months for us to author a really good thing. We're actually pre-authoring the auto grader into Prairie Learn, and we're testing it now in Prairie Learn so that when it's all done, we push a button, it's all graded, and there's no regrades. It'll just be locked in. It'll be right or wrong, and we lock it in, and we'll have a lot of small parts. If you think about this, I think it's 60 total points. I think that's right. So it's just basically a lot of small points, 1, 1, 1, 2, 1, 1, 1, 1, 1, and each one is just right or wrong, and we'll do this. So they won't. And by the way, this is an important piece of the C and Risk 5 part. It's going to be a fill in the blanket thing. You will not be asked there's just no time to ask you to go to C or go to Venus and code something and bring it back. It's not what we're asking you to do. It's more the standard kind of exam questions you've had on paper, which is, what is this line? What does it do? What's this line? Multiple choicey thing. It'll be kind of small pieces of snippety code that is, basically has a single answer, and it is just going to be right or wrong. So that'll be good. No regrades for that. It's not going to be, well, I had an answer that's here. It'll be something that there is no other way of doing other than what we've had. That's the idea. And each one will be like a 1-point question. So if you get it wrong, it's not like it's a 20-point question you get right or wrong. There's only 60 points to go out. And if you look, there's a lot of questions we're going to have. So it's going to be 1 point here, and it's going to be 1 or 0 for these small pieces. That's what we're kind of doing.
We are running quite a bit over time. There is a quick question. If students are taking pass, no pass, and there are also questions, I think on Piazza related to that, do they have to take the final? I mean, it's not a requirement. If you
right, we do have total course points. We have total course points that Stephen has built, which will give you a sense of your total points. And by the way, we can't take points away from you, even if everybody gets an A. We love that, right? So if you've earned a certain number of total course points above the passing bar, that's it. We're not going to lower raise the limit for what a passing number is. There's a passing number. I forget what it is. I don't have it offhand. But if you're above that, there are many classes you don't have to take. Yeah, whatever that is. Yeah, if you're above that and you're past that pass, you're done. You don't take the final. So that'll help your own stress and your own that.
I do want to make one more point about pass, no pass. I don't know if you guys, there was a lot of stress about grades, and that's natural this semester. But just keep in mind that our grade distribution, as Dan mentioned early on, we have about 2/3 of a class in the A- range. when you're considering
never
pass,
happened
no
before.
pass,
Never
think about
happened
that.
before,
Yeah,
by the way.
think
Never
about
happened before. The number of students who are kind of going to the finish line with basically A's and A minuses and A pluses, we've never had the fraction as this semester. You guys have crushed it, crushed the midterm, crushed the projects. Go ahead, Boris. Sorry.
So yeah, exactly. So and in order to get a pass, you need a C minus. So there is, unfortunately, there are people who are not doing well and not in a passing range. We're going to give them incompletes if they can fix this. If they can, get some part of a course redone and done better, I think, we are definitely going to help out with that. But keep in mind, there is a very small number of, majority of the class is doing well. So, if you're getting an A, just take an A, don't take a B. That's all that I want to say.
Right. Yeah. I mean, you definitely look at your total course points and see how you've done. And if you've done well on the midterm, that clobbered your quest, basically you've got this material. And I think you could probably get an A if you're doing very well. So don't give up the A if you don't take a P if you can have an A. I mean, that's if
Yeah, and I've had people completely freaked out saying, "Oh, my course rank is like 800. I'm doing terribly." Yeah, you're in between A minus and B plus. I wouldn't call it terrible.
Right. I mean, this is one of the classes where you've done so well as a cohort that you could be way below average, but still be getting some kind of A, B thing. I mean, again, we're not taking grades, but we love that. We think we've done a good job if everybody gets an A. I think the midterm was just as hard as every midterm, to be honest. I think we're trying to do the final the same way. We're not trying to do anything different. So that's the space. So think about that. So let me just do some quick answers. Franklin asks, is the final exam strictly inside the time window? It's inside the 24-hour time. You have a 24-hour time window on Thursday, December, make sure I get the date right, but just Thursday, December 17th. And it's not between 8 and 11. That's the official Berkeley one, but we're sensitive to time zones and all those things. You got to make sure it works anytime in the 24-hour window. And you have, again, 3 sections worth roughly those times. Perfect. Ryota asks,
those are our alternate times. Those are our alternate times. They're
exactly.
all on the same day.
Exactly. We give you alternate times and you make it work within your whole day. That's the idea. We'll be, and but there's no other day. That's it. There's no other, like, I can't take it that day. That is the day. Sorry, that's the day. And we give you 24 hours to make it work within that day. We'll be allowed to use C. Right now, you are not. Right now, where the idea is it's more like it'll still be open notes, but you won't be able to use C or risk 5. It's just, we'll ask you to do something and it's there, and whatever, you can pull up a reference material, but you cannot use C. Like, I remember some of the questions before, like in the float, you couldn't use C as a calculator. Here, you can't use C for the C questions. You got a C question, go do it. You can't use C to try to test it, see if it's going to work. You got to do it as if it were a paper exam. So there's that. Adam's asking about midterm retakes being graded. I think we were close to having that done this week. I think that's what that's our current plan.
It's almost done.
Yeah,
tomorrow,
it's almost done. Yeah.
Sorry,
so that's
these things do take forever.
And the midterm grades you saw went out, and the midterm retakes are still in that loop. And it's the same group of people. It's the same core elite group of people who are helping us write the final and helping us grade the last, auto grade the last one. So it's leaning on them a lot, and they're very overworked. They're way overworked this semester. So they're getting to when they can, and we'll try to get that done. But definitely, look, we're going to push them because the 4th is pass no pass deadline. They need to know that they need to get that done before the 4th, so you can make an informed decision about whether you should pass or pass this course. So they know that there's a really hard deadline for that, and that they're working as hard as they can to get that. Let me look at other things. Total course points count as an A. Go look it online. That'll see whatever that is. It's on the policies page. Real coding questions. There may be a coding question where you have to fill in a lot of blanks. You could be like, the old midterm, the old final exam risk 5 questions were 10 blanks and you're writing risk 5, but you don't have Venus. That might be what we're doing this semester. There might be lines and lines and lines of writing C code. You might be doing that. You just don't have C. You have to write it by hand. So that's a piece of that. We're going to try to do it. If maybe it's multiple choice, maybe it's not, maybe you're writing it, but that's the space. And our code can actually do the grading of it automatically. So that's the current way we're thinking about that. Again, you cannot be using C or risk 5 outside of the exam window. You've got this thing, and we'll be very clear what you can't use. And right now, none of the C or risk 5 questions have you using Venus or C at all. You've got to do it on paper as an old school paper thing.
One comment about TCP, right? I mean, the EPA points and this extra bonus point that we're offering for filling out the questionnaire go on top of that, whatever it is.
Oh yeah, that's right. Yeah. There's There's APA point. By the way, you don't know this, and it's not in the TCP, but we're going to have APA points, which is an internal number. I think we talked about that in our first lecture. It's an internal number our TAs are giving you for seeing you do effort, participation, and altruism. That sprinkles on top. You don't see that until the end. You never see that number. You just have a final number that's internally what grade you get. But there's a sprinkle invisible number that you get on top of that. Then there's also extra crediting points for doing these extra performance for projects, the performance part of the projects that are fully volunteer. You don't have to do it, but if you do it, and you can get some sprinkle points there. And on top of that, if 90% of you fill in the survey, nudge, nudge, wink, wink, say no more, do that survey. So course evaluations, Berkeley DU board, already remember the URL? I think it's like that. Course-evaluations.
Everybody should have been emailed.
Yeah. So you should all be emailed. Check that email. Look for course evaluations. If 90% of you, by the way, I need students to and remind their friends who are not listening to this or not reading Piazza. We're going to try to share this with all the Piazza. If you fill that in, that's not one more point for extra credit on top. All those are on top of it. All those are on top of TCP that you're getting. And people asking about, will you know the clobber? You could, if we don't get it by the clobber, I think that Steven's working to try to get it in, but if you don't get it the clobber, you could manually compute it. You just put it in and figure out the number and figure out the thing. We'll try to have some standard deviations out there so you can do that work yourself, but it'd be better if the software did it for you to get the raw number. So hopefully that's there. I'm good. I don't see any other open questions.
He said he was going to get it done before the final.
Yeah, and they need it before the 4th, really, because they need to know before past deadline. Okay.
Yeah.
All right, folks. Again, overall, you're doing great. Keep up the good work. We're going to, yes, anonymous attendee, we're going to try to remind people to do that continually. And by the way, the only thing right now, all I can see is the percentage of students who are in right now who've done it. So all I can share that. I don't know, Bob and Sue did it and Ralph and Jaime haven't. I don't know that. All I know is, and by the way, just so you all know, none of us I can't see what you wrote. So be very honest, be very frank. It's anonymous. I can't see what you wrote until my grades are in. So none of us can see what you've written about it. So if you say, Dan was terrible, Bor was great, whatever you say, I don't care. I do care, but I can't see it until all the grades are in, and then it'll never affect the grade. So say what you need to say, give us the feedback. Please tell us we're great or how we can improve. Put that stuff in, and then that closes, and the final, and by the way, that closes on Sunday night before final exam. This is important. This is another reason maybe why they didn't want to have exam before that, because they want to have the evaluations happen the Sunday midnight, and then exams happen, and then grades happen, and then we can see the results of the evaluations that happened like a month ago. So it's kind of this weird thing. So we don't get to see what you said, and we will never be vindictive. We were angry. You said we were bad, and so we can't do that. Whatever the grades go in, and then we just get the results. So please, honestly, it'd be better to give us improvements. What can we do? I know a lot of things worked and didn't work this semester. We know most of those things, but if there are other things, we give a huge feedback form. If there are other things that didn't get say or something happened since the last feedback, please do this. And I believe CC had another form of asking about Prairie Learn specifically. We may end up having a small other survey. Please do.
Yeah, we're going to have. I think we're going to have another survey. That would be,
right. We're learning so much.
Load this campus survey heavily with our custom question.
Right. We didn't put you can only ask 4 questions in that, and it's not enough. It's not enough to ask all the things we want to know about how to improve this class overall. So
so if you can give us reasonable feedback, suggestions, we will very much be interested in those.
Thank you. All right, we got to run. Thank you so much, folks. We'll make sure to share this information on Piazza. See you. Good luck, but please do come on Wednesday.
It's already on Piazza. Yeah.
Oh, perfect. Please do come on Wednesday and come on Friday, both live. We'll see you live again on Wednesday. Thanks, everybody. Take care, folks. Bye.
Thank you.
Tell your friends to come too. Okay, bye.